In the Spring Constant Lab, we are going to study a simple mechanical system in order to revise skills and techniques from previous courses. Our focus, therefore, will be on the presentation of data and handling of uncertainties, and as well as keeping a logbook. The aim of this lab is to measure the spring constant using two different methods. In the first method, you take a spring vertically at rest and you put a mass at its end and measure the displacement induced by the weight of the mass. And this, according to Hooke's law, is related to the spring constant. So we see that we can get the spring constant K just by measuring X for a given mass M. Note that x is the displacement of the spring induced by the mass when it is hanging vertically. So that's not the same distance you will have if the spring was horizontally because of the mass of the spring itself. The second method involves an out of equilibrium measurement. So if we pull the mass down and we release it, it will oscillate with a frequency t, which we can relate to the spring constant K. Note that the mass big M is not exactly the mass we've put at the end of the spring, small m. That would be only the case if we could neglect the mass of the spring itself. But usually it's not negligible, and therefore we need to take into account in the effective mass big M, both the mass of the spring and the mass we put at the end. So we have two methods to measure the spring constant. One is to measure the elongation x, and the other one is to measure the period of the oscillations t. And these two measurements, we need to compare them and see if they agree with each other. So in principle, we only need one measurement per method. That will be enough to determine the constant k. In practice, that will lead to poor results because they will be associated with large uncertainties. So we need to use different masses in method one and to repeat the measurement in method two in order to reduce uncertainties in the final results. So let's now talk a little bit about uncertainties. For instance, if we take the first method using mg equal kx coming from Hooke's law, we see that in order to determine the spring constant k, we need to measure x for a mass m, and we need to know g. But all these quantities, m, g, and x, have an uncertainties, and therefore we need to determine from these uncertainties what will be the uncertainty for k. And of course, some of the uncertainties will be large and some can be very small. For instance, we know relatively well what is the value of the gravitational constant G in Canberra, and its associated uncertainties could be relatively small compared to the others and then could be negligible. However, whenever you neglect an uncertainty, you have to explicitly explain why it is the case and justify this assumption in your analysis. Also, giving an uncertainty is not enough. You also need to say how you got it. Maybe it comes from a previous measurement, maybe it comes from well-known data, maybe it comes from theory, or just you determine it yourself. So let's take an example of the mass m entering Hooke's law. One way to determine sigma m is, of course, to weigh it on a scale, and then the uncertainty will be given by the precision of the scale itself. Alternatively, you can also use different masses for which you know the actual uncertainties, which can be given, for instance, or provided by the manufacturer. So let's take this example where your mass m is actually the sum of individual smaller masses. In this case, this is actually a simple application of what we saw in the video on analytical propagation of uncertainties, which you can find in Wattle in the lab section. So once you have determined sigma m, this also gives you how many significant figures you need to give in your value for m as a final result. For instance, if your sigma m is 1 gram, no need to go beyond 1 gram in the value for m. No need to go into milligrams or micrograms. That will be completely irrelevant. So another thing we want you to be careful in this lab is the way you plot your data. So if you have measured the quantity y for different values of x, it's important that you label your axis properly and you plot your data accordingly and with the corresponding uncertainties as an error bars. And usually you have error bars both in x and in y. If for any reason one of these error bars is much smaller, you need to specify it and only plot the one which is relevant. And of course, if the quantities you are plotting have a unit, it's important that you specify these units on the axis. Another thing we want you to do in this lab is to compare two values. So in general, when you want to compare two values, for instance, two experimental values made by different teams or from different measurements which you have done, like in this lab, or if you want to compare an experimental measurement with a theoretical one, you need to find a way to conclude if these values agree with each other or not. So let's consider two values for the quantity A, A1 and A2, both with their own uncertainty, sigma A1 and sigma A2. What matters, of course, is the absolute value of the difference between A1 and A2, which measures how far they are from each other. And we need to compare that with the associated uncertainties for this difference, A1 minus A2. And you will consider yourself happy, or basically meaning these two values agree with each other, if this difference is actually smaller than a given number n times the sigma of A1 minus A2. And this value of n depends on the field in which you are. For instance, if you're in social science, in astrophysics, in physics, etc. In physics, we are relatively picky and we usually require n to be relatively small and usually not larger than 3. Now what we need to do is to give an expression for sigma A1 minus A2 as function of the uncertainties we know, which are sigma A1 and sigma A2. So you have access in WATL to some notes on uncertainties, and in particular, if you look at the section on uncertainties for sum and differences, you will see that sigma A1 minus A2 is just the square root of sigma A1 squared plus sigma A2 squared. Last but not least, we want you in this lab to start using logbooks in an efficient way. Logbooks are very important in physics and in science in general because you want your experiment to be reproducible by others. So it needs to be clear so that others can actually read it and repeat what you did. So all the information, all the relevant information needs to be there. So it needs to contain some basic information, such as your name, the name of your lab partner, the date you did the experiment, the title of the experiment, and this needs, of course, to be clear and legible. Keep in mind that this you write for others, not just for yourself. The logbook should contain some clear aims of your experiment. What is it that you are trying to reproduce or to investigate? You need to have a clear description of the method, how you do things, and also how you intend to reduce uncertainties. You need to give clear diagrams of your setup, again, in such a way that it could be reproduced by someone else. You need to provide also some level of theory, I mean, if it is relevant, not so much that you need to give the theory background behind, for instance, the expression you want to reproduce. For instance, you don't need to give the derivation for Hooke's law. However, if you are rearranging the equation in such a way that it will be easier for you to extract the relevant quantity, for instance, the spring constant in this lab, you need to do some massaging of the equation and some derivation which you need to put in the logbook as well. And of course, you need to give the results. You need a clear presentation of the results. The raw data needs to be there, including their units and uncertainties. You need to give the graphs which you are producing, as well as the final result. So in this case, what is the value of the spring constant you extract? And this need to contain, of course, units, but also uncertainties, and importantly, how you derived these uncertainties. There is some videos and some notes in Water to help you with that. And finally, you need some conclusions and eventually comments. Um, did you manage to answer the initial question which was asked? Like, did you manage to find a value for the Hooke's law? Does it make sense? How does it agree with what you expected? If you did two measurements, do they agree with each other? If you did a measurement, does it agree with other measurement done by other people, or by does it agree with the theory, for instance? And for that, of course, you need to use Three Sigma criteria we just introduced before.